every bond is either ionic or covalent, nothing else, all the rest of the forms are just subforms of the same. For ionic interactions, it was easy enough for us to explain that something easily loses electrons and something easily gains electrons and they live happily ever after, which was our basic model for an ionic bond. But for covalent bonds, story becomes a bit difficult to explain because there is no straightforward electrostatic interaction only. There are nuclear interactions as well, and nothing actually easily loses electrons. That is why the electrons tend to be in between the two atoms, which we call covalent bond. Then we try to come up with models to explain the same. The first model that we came across was the valence bond theory, in which we essentially thought of the wave nature of an electron, where one of the orbitals. Also, let me just stress on this valence for a bit. Bivalence bond was the electrons that are energetically high enough, or basically farther away from the nucleus, for them to interact with other atoms, electrons, and nuclei, are the only ones that actually participate in bonding according to our initial assumption of this theory, which is why we consider only the electrons with the maximum n value of an atom when we talk of valence electrons, and they are the ones that are involved in bonding. When we talk of specific electrons, say this is the representation of an s orbital. This plus essentially represents, when I think of electron as a wave, this plus essentially represents the relative phase that is this omega t term, how this compares to the omega t term of the other orbital. If this and the other orbital's phase terms are the same, they can bond. Basically, they are either plus plus or they are minus minus. When these terms are different, there is a phase mismatch. One is plus and the other is minus, so they can't overlap. That was the basic principle of valence bond theory. And not going into too much detail, you can refer to the previous lecture for the same. When we think of this, we see some inherent flaws. That is, one, we called, when the phases mismatch, we called it a zero overlap. What do I mean by a zero overlap? Where do those electrons go? Where do they stay? The portion of the destructive interference was not very well explained by valence bond theory, which is an inherent flaw in it. Second, we saw that when molecules, I'll rather use a chalk here. This chalk was a yeah. When we were yeah. So zero overlap. When we were talking of, what was I saying again?
Destructive phase not elaborated.
Yeah. So basically, when phases go, the inherent flaw in valence bond theory was that it doesn't consider or explain in a rather elaborate way that what happens to that electron density that is destructively interfering. That was the first inherent flaw in it. Second, we certainly observed some things. We certainly had some experimental observations for molecules like this molecule, if this carbon atom, as we discussed, the orbitals that are going to be present for bonding are labeled as follows. But when we consider the actual overlapping picture of these orbitals, when they combine with the 1s orbital of the H, these bonds seem to be very different from each other. in terms of their symmetry, in terms of their energies, they seem to be very different. But when we see experimentally, these bonds turn out to be identical. These bonds turn out to be identical. That's why we need a better model to explain the same. Then to address this very flaw comes in the model of hybridization, as we discussed in the last lecture. What hybridization essentially does is it essentially considers all these orbitals as wave functions and checks out their sum. When these orbitals are summed, their wave functions are summed, it essentially divides it by 4, and that is when 4 orbitals are involved, it essentially divides that sum by 4 and spits out a unit orbital, which basically can represent which can represent one of the 4 equivalent energy orbitals or equivalent symmetry orbitals that can further participate in bonding. That takes away the mismatch that we were thinking of in terms of the different bonds that makes all of these bonds identical, both energetically and symmetry and in terms of symmetry, which solves our problem. Also, when we talk specifically about methane, we have got carbon here. Carbon has 2s2 2p2. And I try drawing it following all laws of electronic configuration, and I try drawing it. We see that these orbitals, these are not essentially the same in terms of their basically their electronic arrangement as well. So what we need to do is first we need to make them similar in terms of their spin, or basically the electronic arrangement that they have, so that they can further combine.
Exactly.
So yeah, basically this electron needs to go here in order to make these orbitals electronically similar. Now this going here, if you think about it, this is a low energy state, this is a higher energy state. This transition, or basically this transfer, requires some amount of positive energy, which basically would be in theory would be compensated by the latter negative release after the formation of the entire molecule, which is what we say in theory. When the example that I gave in the last lecture, say something A forms something B, this B has to form something C. If A to B requires energy, say it requires A amount of energy, this releases 2 amount of energy, then the whole process becomes spontaneous in the sense that this energy input is essentially compensated by this one. So yeah, the one of the inherent flaws that we were talking about is still not addressed here. That was of destructive interference. That is something we are going to talk about now. What happens when electrons don't overlap? Basically, those wave functions don't overlap because of their mismatch. What do you think intuitively should happen? I'd like some answer.
Electron density will decrease.
Decrease in what sense? Where will those electrons go?
To their respective molecules, to their respective nuclei, something.
Yeah, because let me tell you, those electrons never came into that place. Just because of their phase mismatch, they could never come in between those atoms. That is why they stay concentrated towards their nuclei. That is why you see. I'll show you those simulations in this sense to explain the same. Now, how do I classify these interactions? These two types of interference. How do I classify them? Basically, if the phases match, then we call it constructive interference. Now, essentially, what constructive interference is going to form is a place where electrons stay. Where do electrons stay? Electrons stay in orbitals. what are these orbitals inside now when a molecule is formed? They are molecular orbitals. Very intuitively, they are molecular orbitals. That is where the electrons are going to stay after the formation of the molecule. And when phases match, the electrons are actually between the two atoms, then we call it a bonding molecular orbital. Or maybe you will hear the abbreviation BMO for the same. That is when this constructive interference, the idealistic constructive interference would happen, then we'll get a bonding molecular orbital. But when a phase mismatch happens, that is a destructive overlap, that would imply that the electrons stay close to the respective nuclei. A's electrons stay close to A, B's electrons stay close to B. That is when we talk of something called an anti-bond. Basically, as it's exactly the opposite of what we see in terms of bonding, hence we call it anti-bonding. Hence we call it an anti-bonding molecular orbital. You might hear the abbreviation ABMO. Now, something that we maybe I have not elaborated on that much yet, but the orbitals, when they overlap, their energies or their amplitudes should be kind of similar. They should be in some sense overlappable. They should be one of them should be too high or too low with respect to the other for them to overlap. That is, along with a symmetry match, there also should be an energy match. Now, why is that? Let me tell you. If say when we talk of when we think of orbitals, say I represent an orbital here in terms of energy scale. Say I represent an orbital here. Say I represent an orbital here. Now, if this gap is too much, what is going to happen if they if they want to overlap? This orbital comes a bit low. This goes a bit high. Now, if it has to come too high, that requires too much of an activation energy thermodynamically. And as we talked of in the first lecture, all that is spontaneous when we are not talking about entropy is in terms of energy. When it requires too much of energy for this low-lying orbital to come above, that essentially disfavors bonding. That essentially disfavors their overlap, which is why matching energies are a requirement for overlapping orbitals. So the two criteria for overlapping. Energy match and a symmetry match.
And we also say it has to be within the same phase, because if it doesn't, it will
We talked about phase. We said that omega d term must be the same for both these orbitals for them to constructively combine, and if that omega d term is not basically opposite of say it is opposite for one with respect to the other, it won't overlap. It would be a destructive interaction. Yeah, that would form an ATM. So energy match and symmetry match. Now, if you notice, this is something we have directly borrowed. This is something that we have directly borrowed from the valence bond theory. So it was not a waste of time after all. It is, it is very helpful in terms of getting the physical meaning of how orbitals overlap, where electron density actually resides, which is rather a very funny thing to say because we don't know where an electron is, we cannot see it. So yeah, but this is something that we borrow directly from the valence bond theory. The only thing that we add essentially is we explain destructive interference and also a few intricacies that I'll be discussing as we proceed further. I cannot dump everything at you at once, right? There are also SMOs. We will be talking about them as well. So yeah, when we think of the simplest molecules around us, we just go from the corner of the periodic table and we start adding electrons because there we first think of just one bond, that one line between two atoms. When we just think of the simplest case, we think of say going from hydrogen to helium, lithium, beryllium, and we go on to say keep adding one electron, and they're basically homonuclear diatomic molecules. That is something that is the simplest case in order to build a model from scratch. Homo means both the nuclei involved are the same. Diatomic means that we are talking about only two atoms involved. Okay, so now when I talk about homonuclear diatomics, let's start with the simplest example. Think of the hydrogen molecule. Now, from the classical valence bond theory explanation, you would have thought of this as H being singly bonded to H. This thing gives 1s, this thing gives 1s. Both of these happily overlap and it stays in between them. Now, when we try to say represent this in terms of molecular orbitals, what do? We think of H2 we think of hydrogen. What does it have? It has one electron in its one orbital. One orbital, that is one s. That is what hydrogen is. Now, what I'll be doing is I'll be drawing orbitals in order of their energy. I'll be representing those gaps. Those gaps would essentially represent the energy difference between orbitals that I'm going to draw. So yeah, if I bring a hydrogen here, if I bring a hydrogen atom here, and as this hydrogen and this hydrogen are the same, these 1s orbitals are going to lie at around the same energy level. This is an axis of increasing energy. Now we start thinking of possibilities, because those phases are going to change with time. Those phases might match, might mismatch. So now we'll be thinking of possibilities. What if the phases do match? If the phases do match, then they essentially, these orbitals combine in order to give you a lower energy orbital, because they are now staying happily between those two atoms. That nucleus attracts the electrons of the other atom. This nucleus attracts the electrons of this atom. So they happily stay with that negative potential energy that they have generated. Now, these two orbitals form a PMO. Now, what do we call this PMO? We borrow this from the valence bond theory. What does a 1s and a 1s orbital combine to give? They combine to give you a sigma bond. What do you call this orbital then? You call it sigma. Now I call it sigma 1s. This is just a notation. I could have also called this sigma 1 or just sigma, just plainly sigma. This is just for representational purposes that I am calling it sigma 1s. Now, the other possibility that we were neglecting in the times of valence bond theory was this. Now, the star is just there for representational purposes. This is an ABMO. This is an anti-bonding molecular orbital. This is where electrons probably could be. when these two orbitals combine. But now, as we think of possibilities, we also need to think about the rules of electron filling. Where would electrons go? Electrons would try to be in the lowest energy state possible. And we have now, as these orbitals, these are now practically non-existent to us, because these are the only orbitals that are existing when a molecule is already formed. Then we think of the configuration. How do you think of the configuration? Start filling in from the lowest energy level possible. Now, when you see, you put one here, you put the other, you reverse the spin. You reverse the spin in order to preserve our Hund's rule and Pauli's exclusion principle. You do all that. Compound rule is something that we have followed while we were filling it in the lower energy orbital. Now, this is where things would get interesting. Now, when I replace this H2 with He2, this is not something that we have seen. This is something, because we are building our model. We are trying to think of a model that explains molecules that we might not even have seen from the initial data that we have. Now, He2, something that you have not seen, you would expect it to look something like this. But something you have not seen. Maybe there is a reason that you have not seen it. Now, when we think of it, this is not 1s2, 1s1, this is 1s2, this is 1s2. When these two electrons stay here, now we have got 4 electrons to fill up. Now, when we have got 4 electrons to fill up, we've got electrons here. We've got 2 electrons in a lower energy state and 2 electrons in an equivalently high energy state. If this gap is say delta x, then this gap got to be delta x as well. Now, why am I saying this? I am saying this just because these two orbitals, these two atomic orbitals are at the same energy level. So when they combine in say completely constructively, then they are going to match completely, which drops them to a certain level. But when they combine destructively, the same orbitals from the same energy level, if they combine completely contrary to that, then they are going to rise up in energy in the same magnitude. Now, when we think of this thing represented electrons being between the two atoms. Now, this thing represents electrons being concentrated towards that nuclei. But now, when we think of it in energy terms, 2 of the electrons stay in very high energy, 2 of the electrons stay in say a very low energy state. When we see that from far apart, we see that the energy in net becomes 0. The energy of the system in net becomes 0, and hence the system doesn't really exist. Because for any system to exist, there must be some potential energy. I would just rather say this. If this is inversely proportional to R, this R, unless it says until and unless this R becomes 0 or something, this R is always going to be non-zero. So there is always going to be some non-zero value of energy if a system exists in some configuration. But if this system does not exist, then the energy got to be 0. Then we don't have to follow this, because the system doesn't essentially exist. That is how we conclude that He2 doesn't exist. Now, to maybe generalize this to a next level, we think of something called bond order. Now, say when we talk about these energy magnitudes, say something is, say the bonding orbital is much lesser and the anti-bonding orbital is much higher, and these differences are not the same. There is going to be a competition between these two, and the net result would depend on these gaps. how large or how small these are. If the gap, if say the anti-bonding orbital essentially goes way high, then we say that the bond order term decreases, and when we think of this going too low, we think of bond order term increasing. Just say this, and to see in terms of this homonuclear model, as these magnitudes are not going to change, as these orbitals are always going to be the same in energy, we try to come up with a simpler formula rather than seeing the energy differences. We come up with a simpler formula. We say that the energy is going to be kind of proportional to the number of electrons that are staying in an orbital. Then we think of number of bonding electrons, number of anti-bonding electrons, and we subtract them, and as we are talking about the same electron, to check the energy difference, we divide it by 2. Also this comes in because of the say inherent assumption for that we carry forward from the valence bond theory, that a bond involves 2 electrons, but that is essentially one bond. So when we try to connect this to the notion of number of bonds, you need to divide this term by 2, and then you call it bond order. This is not the most general relation that you want to follow, because the most general relation would be the energy difference between these 2 orbitals that are formed. But because of to make it convenient for us when we are talking about homonuclear diatomics, we come up with this formula. Anybody having any issues until now?
Could you just repeat the part about when, because of the destructive interference, the energy becomes 0, the total energy?
Yeah. So if a system exists, these 2 electrons, these are going to stay between those 2 nuclei. These 2 electrons are going to stay concentrated at each nuclei. When we think about the interaction energy that is formed by this bond, those 2 electrons staying behind rather than maybe lowering in energy, that compensates for this bond. That essentially compensates. When you think of potential energies, you can add them, right? You can add potential energies. When you think of computing the total energy of this whole system, you add these 2 energies. When these 2 energies these add up to 0. And no system that exists has energy 0. Everything has a 0 point energy. That is why that is something that we inherently hold as an axiom. If a system has to exist, it's got to have some form of energy.
So are we assuming that the isolated helium atom, then that will have 0 energy? Is that the assumption that you are making? Because then shouldn't the 2 energy, shouldn't they cancel out and reach the level of the isolated helium orbital?
I'd rather say that this is a helium atom. When we were talking about an isolated helium atom, this electron density was also new, right? Then this was not the gap was not good enough for these 2 to attract. But when this comes in between, their interaction kind of changes as well. These two things that we are talking about. When they come in between, you have studied that, right? Neutral charges and all that. When you think in those terms, the energy when you add all these interactions, you essentially add all these interactions. That turns out to be 0 because the system is symmetric. The energy that lowers from this middle interaction
is increased.
That got increased from the anti-bonding interaction. That is where you come up with this. Yeah. Now the point that we have reached this is somewhere that we stop caring much about geometry and leave it to computational techniques. There are many of them. I forgot the name of one that I was about. AB initio. There is a technique called AB initio that talks about geometries, because we have made everything mathy, and we have made everything, and we have represented everything in terms of math. You won't see everything physically. So it's better to rather leave that to the computational chemist to do. What we are trying to do here is representing everything in terms of energy. Now, we talked of helium. Now we'll talk about lithium. Similar to it, not very different. Now, when we think about it, this one is so these valence orbitals are now going to combine in the same fashion that we did for He towards the H that we talked about in our model. Now I should rather draw these a bit higher. These part of my drawing. Yeah, this is the same gap. Yeah. So when we start filling electrons now, we start filling from here. We fill 1, we fill 2. Now when we start thinking about it in terms of, we pause for a second and we think about it in terms of the bond order. This bond cancels out this bond because this is a sigma star. This is a sigma and sigma star. Because of all the fiasco that we did earlier, these two essentially cancel. These two. But after this, another interaction happens. I'll call it sigma 1 star. Now, this interaction causes another bond to form. This bond in the conventional sense of valence bond theory that we have taken, this is a simple bond between Li and Li. So yeah, basically if you need to say figure out a pattern, you can think of it. This is very consistent with the valence bond theory interpretation if you think about it. These two, as a whole, these 1s2 electrons, because of not being the maximum n, they were not involved in bonding. This is very much consistent with the initial assumptions that we had in our minds. That was not all to waste. Now when we think of one more electron, we go to Be2. One electron gets added, and the same fiasco that happened with He2 happens here as well. This molecule also doesn't exist because the energy is going to become 0. Yeah. So now the things get a bit complicated that we are going to discuss. We'll need a primer for that. We'll need to address a topic called sp mixing. Now, borrowing the same assumption from valence bond theory as we set up, we really established that when, say, two p orbitals to say the least, because p orbitals are going to get involved now when we go to boron. Two p orbitals, when they combine head on to each other, they overlap this much. But when we think about it in terms of a sideways overlap, they overlap a bit less. These overlap a bit less than what they would for this. So technically we can say that a sigma bond has more overlapping extent when overlapping extent is more, electrons are overlapping more. Essentially, the electrons are going to stay more between the atoms. As long as they stay between the atoms, the bond becomes stronger. That is why this also gives us a notion of the fact that bond becomes difficult to break. Rather, I would say difficult to break. Difficult to break in the sense that if potential energy of a system decreases very much, you need to supply much higher potential energy for it to become zero or even higher if you want it to. That is why it becomes difficult to break. That is when we define the term of bond strength. When we think of bond strength, then also because of this direct relation that we see, we say that sigma bonds are generally stronger than pi bonds. Also depends on what orbitals they are forming between, but essentially this is the trend that we observe for this reason that we borrow from valence bond theory. Now by this, when we start thinking about B2, diboron, I write the configuration of boron for this P thing comes into play. Now, when we talk about overlapping of orbitals, what do we essentially expect? We expect if I have not mentioned earlier, I am considering the z-axis to be the internuclear axis. Very conventional, but I feel like I should have mentioned it. If z-axis is the internuclear axis, then pz and pz are going to form the sigma bond that we were talking about before this. Now, if I think of this z as my internuclear axis, then what we should expect is that pz when it overlaps with another pz, it is going to be lower than when a px and a py overlap. We expect it to be lower, but we see something very weird happening. We see that that when we talk of overlapping of the lower thing remains the same, so I'm not rather drawing it. I'll draw 2s here. From one of the boron atoms. Now, when I think of this, I should rather expect when these orbitals overlap, I should rather expect that I should expect something like this to happen. Because I should expect something like this because of the reason that we elaborated on earlier, that sigma bonds, sigma overlaps are stronger or say more in overlapping extent than pi overlaps. So this thing should be lower in energy. But what we see is that for boron, this thing is not here. This thing jumps over here. Now why is that? Now we introduce something called now sp mixing. Now the thing that I was talking about to you earlier, the question remains which S and which P. Which S and which P. What I thought of, I would like to, I would like you to point out the flaw in my argument that I had earlier in my mind. I thought of this as, when I thought of this, I had this reasoning made up in my mind that say that the mixing that we are essentially talking about, the gap in energy, because the energy gaps in these atomic orbitals in this sense are very less. When we talk about very less n values, these gaps are very less because nucleus is very they are not very far away from nucleus. So all of them essentially experience very similar effective nuclear charges, which is why these are very similar in energy. When I thought of this, I thought there is a 3s here, I thought there is a 2p here. If they have to mix somehow, that we are talking about sp mixing, if they have to mix somehow, this comes a bit lower, this goes a bit higher, and hence the pz thing essentially surpasses the px equal py thing that we are talking about. I didn't mention that because the overlapping extents for both of these are the same. That is why their energies would remain the same. This would be called a pi set when they overlap. But now the point that we were talking about, what is the flaw in this reasoning? If you can tell me that if this 2p goes a bit high, 3s comes a bit low, then this 2pz would go a bit higher than this. What is the flaw in this reasoning? This is something that I believed earlier, but it is not true.
2pxy and 2py can mix with 2s, so that 2pxy and 2py energy will become lower and it will come down.
The problem is we talked about two things: energy match and symmetry match. S doesn't have a symmetry match with py and px, but it has a symmetry match with pz. When you think of this S also has a symmetry match with pz, and energies are not very far away. Which orbitals are going to mix? Is it 2p 2s mixing, or is it 2p 3s mixing?
2pz and 3s.
Because of this, the assumption that we had in valence bond theory, this can bond with this. These are along the axis, right? These cannot bond here, because this is a node. There are no electrons here in order to interact. Now, what do you guys think?
3s and 2pz.
3s and 2p. That's what I exactly thought, but that is wrong. I am asking you for to point out a flaw. Then we'll give a break, and then then you ponder about it. Then I'll say give you an answer after the break. So I'll continue now. Yeah. So as we discussed, you got me there. When we think about 3s, when we think about boron, 3s doesn't have any electrons, and when we talk of boron, hence talking of the existence of 3s in itself is meaningless, because an orbital only exists if there are electrons. That is just a state for an electron to exist. That is why talking of a 2p3s mix, although they give the same consequences as a 2p2s mix, feels meaningless. Now, what we are going to talk about is the 2p2s mix. This is what we are concerned about. Now, that is also because the gap when we talk about lower elements, lower atomic number elements, this gap is very less. It keeps on increasing as you increase Z. As this thing keeps on getting pulled more and more inside, this gap increases. Hence, we don't see this effect after a certain point. Now, what we were talking about, what we expect rather, is for this to happen. If I say sigma, if I say sigma star, if I say pi star, pi1 star, pi2 star, if I say pi1, if I say pi2, we are expecting this thing to have this fashion, but this doesn't have this fashion. This sigma gets pulled up. Why does it happen? Now, when we think of it, the energies also represent how far or how close the electrons are. When we are talking about their position between two atoms, because energy, this dependence that we are talking about multiple times in our lecture. This dependence directly relates energy to distance. Now, when we talk about 2s, when we talk about this, I would say sigma naught and sigma naught star. When we think about this, these electrons, if I fill it just the way I do, just the way I would have, if without assessing the properties of the orbital of boron, diboron, I'd rather fill them like this. But now the problem comes in. These orbitals, because of being too close in energy, this bonding orbital and this anti-bonding orbital and this bonding orbital, these are too close by now, and hence as electrons repel, because energy inversely relates with distance. These are too close for them to exist this way now. This thing is going to get pushed. This thing is going to have a bit higher energy. That is the penalty that this molecule pays for this 2pc and 2s to combine. These two combine to give a bit lower energy orbitals. These two combine and decrease this gap even more, which forces this sigma star to go up. Are you guys getting it? When we talk of mixing, this 2pc comes a bit down, 2s goes a bit up. This thing and this thing are now going to repel a lot more than they would have previously. When they repel a lot, the sigma star gets pushed away in order to compensate for that penalty that we are paying in order for these orbitals to mix. That is somewhat similar to the hybridization idea that we talked about, but we don't call it exactly hybridization. It is called a second order orbital interaction. So ST mixing, when we are talking about it, we are talking about the second order orbital interaction. And because of this sigma star getting pushed up, the order reverses, as we'll see in the case of B2, also in the case of C2 and N2. But when we talk about these things after say N2, we talk about O2, we talk about F2. This gap becomes large enough for this mixing to even happen. This mixing does not happen after N2, as we observe. Also, the evidence for this lies in the fact that diboron is paramagnetic. Also, when we talk of magnetic nature, as you might have studied in our classical physics, that anything that has electrons whose spins are not cancelled out, when we have unpaired electrons, we have some sort of magnetic character associated with them. Those electrons essentially interact with some external magnetic field when we apply it. So if we do the same to P2, this thing interacts with an external magnetic field. But when we think by this model, if this sigma pz thing, if it would have been lower than the pi set, then this sort of an observation would have been made in the first place. So this thing is something that we come up with after having practical observations. So Now when we talk of the correct diagram, it would look something like this. And now, as we have 2 more electrons to fill conserving our Pauli's exclusion principle, Lorentz rule, and everything of that sort, we need to put 1 electron here and 1 electron here. These electrons remain unpaired and hence giving the paramagnetic nature to B2 that it does have. That is where we essentially observe our theory, observe that there needs to be a correction in our theory, which we did by SP mixing, because we also observed the energies being the way they are. Now, similarly, when we think of C2, N2, you can fill up these orbitals further and further. When I talk of say C2, I'll add electrons here. When I talk of say N2, I'm going to add electrons here. Hence N2 is diamagnetic, as you have heard of. Yeah. So that is where we conclude SP mixing, the fiasco of SP mixing. Now, when we go beyond this, the order reverses, which is because the SP mixing thing does not happen at all after this. Now, drawing molecular orbital diagrams as we did just now is something rather trivial for homoatomics, because the energies of orbitals don't differ. If say a constructive overlap has to happen, only a constructive overlap happens. If a destructive overlap has to happen, only a destructive overlap happens. There is no mix of them. There is no character, as per we say. There is no bonding character or an anti-bonding character to a molecular orbital. They are purely bonding and purely anti-bonding, as we are talking of now. But when we talk of heteronuclear diatomics, both the atoms are different. Then the orders of energy levels, say energy levels of atomic orbitals, are going to be inherently different. Oxygen is more electronegative than carbon. Oxygen's inner orbitals are going to be more penetrating than carbon because of its inherently more electronegative nature. Which is why the gap, which was initially 0 for the same orbitals, won't remain the way it was. When I try to generalize, as electronegativity increases, energy of orbitals, rather electrons, this is something that is going to rule the entire regime of heteronuclear diatomic molecules, that is going to rule the entire regime of coordination chemistry per se as well. This is a very fundamental principle of that. Now, I'll talk about the simple heteronuclear diatomic molecule and leave you guys in the next lecture when we talk about the curious case of carbon monoxide, as you find it very horrifying. So yeah, now I'll be talking about a very simple molecule, HF, hydrofluoric acid. Don't drink it, please. So when we talk about HF, there is a hydrogen atom involved. What we are going to do, what we did in the case of homonuclear diatomics, essentially the same thing applies. When we think of hydrogen, we think of a 1s. When we think of say F, What do we think of? We think of a 1s, a 2s, and a 2p. But this thing being in one corner of the periodic table, this thing being in the another corner of periodic table, this thing is much more electronegative than this is. So the orbitals, as we initially stated, the orbitals are going to be much lower lying than they are right now. So when we think about it, there would be no energy level that would be matching this one. There would be energy levels that are much lower than this. The 2p is going to lie here. These gaps are all arbitrary. They are not exactly the same as I am showing them to be. And 1s is somewhere buried down. 1s is somewhere buried down. It is so close to it that it doesn't even interact. Now the point that this gentleman was talking about would come in non-bonding molecular orbitals. We were talking about them. When I think about H, we think about 1s1. When I think about fluorine, we think about this. Now I'll start filling. I haven't filled 1s, I'll represent it later what it's called, what it would be in terms of bonding now. Okay. Yeah, perfect. So yeah, now as high lying orbitals of F are going to be similar to that of hydrogen. So these are going to combine now. Which of these combines, by the way? S can only combine axially. So 2pz is going to combine. This is something that defines. So we form a sigma, and corresponding to that, we form a sigma star. Now this is where things get interesting. You cannot say that the bond order is 1 now, because the energy gaps are different. You cannot say that it's exactly 1. If you have been saying that HF has bond order 1, you are wrong. It would be kinda you say more than 1, because the orbitals that are the bonding orbitals that the electrons are going to lie are say more in the bonding side than in the anti-bonding side. That also explains certain things that we were talking about classically. This thing donating electrons to the place where there is an electron deficiency. If this guy donates its lone pairs, that we quote unquote lone pairs, if it tries to donate, the bond order is going to increase. That idea is still consistent when we think of this in terms of energy. So that was not at all waste. I am saying this for a millionth time, but that is something that is to be stressed about, so that we don't forget everything that we say had logically concluded. Now, when I start filling up electrons, I fill 1 electron from here, I fill 1 electron from here. What happens to these? They have nothing to combine with. They stay where they are. They are not involved in bonding, but they are in a similar energy. At least these are in the similar energy level. These are in the valence shell. So they are going to stay here and form something called, I'll call them pi NPM. The orbitals are usually denoted in the notation of sigma and pi. That is why I am not just calling them NPM. Yeah, because these, when they bond, they form a pi set. That is why I am calling them NPM. These electrons just stay the way they are. Similarly, the 1s thing, it is much lower, but it stays just where it is, sigma NPM. It just stays the way it is. Now we also compare this to the valence bond theory picture that we had in our minds before this. When we talk of the classical picture, F and H have 2 electrons between them. now you guys know where these guys popping from. These guys popping from. That is essentially that is represented by here. These are non-bonding, so they stay close to F at the initial energy level that they had. That explains the fact that F has 3 lone pairs.
So one thing, the 1s and the 2s are non-bonding orbitals. They are both of them are sigma only, right? Both of them are sigma NEMO. NEMO.
Yeah.
Both the 1s and the 2s.
Yeah. Oh, sorry. 1 second. Did I say 1s? Okay. Sorry. It's 2s. 1s is 4. 2s. Sorry. 1s is even lower for it to interact, so it's not going to interact. It is the 2s that is going to form the sigma and NEMO. Really sorry for the discrepancy that I caused earlier.
So the 1s isn't going to have a NEMO thing. It's just
1s is just going to stay so inside the core that it's not going to interact with the rest of the molecule. Or else say the rest of it won't participate in bonding. Yeah.
When you have said the criteria of overlap, okay, that is energy match or the symmetry match. The both should be implied on all the things or
By energy match, I never meant that the energies are identical. Energies should be similar enough. When you think of say the energy gap that is going to be created, if that energy gap is not too outstanding, if those electrons are not going to be too anti-bonding or too bonding, until then everything is fine. This 1s combining with this 1s is outrageous, but this 1s combining with this 2pz is somewhat okayish, because we are because when we see around us, we see molecules of different atoms. We are not always seeing the same or basically the homonuclear diatomic picture. We are not always seeing that. So to explain that, we got to come up with this model. The 1s thing, yeah. Sorry, I called it not bonding. I'm sorry. This is a mistake I previously made as well. This is the pair of core electrons. They are so penetrated inside that they won't even interact. That penetration effect that we talked about in the first lecture. They are so inside that they are not going to interact.
And what was the full form of NEMO?
NBMO.
NBMO.
That is
non-bonding molecular orbital.
basically this is something that is energetically high enough to interact with the other atom, but there is nothing corresponding to it that it can interact with, so it won't really interact. But it's still a part of the molecule, staying in between, staying somewhere between, say, both the atoms. So yeah, that is why we call it.
Can we actually calculate the bond order using the diagram?
You need to, no, you cannot.
You would have to know the exact energies.
Yeah, you would have to know the energy parameters. Those bond orders would be similar to this. I'm not denying that they won't be they won't be similar to this, but they won't be exactly the same the way you think of them.
So if instead of hydrogen, if we had another atom that had similar energy levels to it, then these non-bonding orbitals would become bonding orbitals.
Yeah, they could. That depends on the case. If they have something to interact with in front of them, they would.
Got it.
But in this case, that thing is empty. This 1s is already interacted with these. Yeah.
Actually, in fluorine, it won't become because fluorine is most electronegative.
Yeah.
So it won't. But in case of oxygen, it can. Like in CO, there is a 3 bond.
But say you bring something, say this 1s won't interact.
It won't interact.
Yeah, 1s
but
won't.
like a 3 lone pair.
Yeah, but if say I'll think a bit if I can come up with an example.
Fluorine only forms single bond with everything.
But have you seen this picture that F sometimes gets a positive charge after it coordinates electron? Have you seen this picture?
No.
This is a thing that is
In this case, it can, but it is existing.
in this, yeah. The point being that we can theorize stuff, and also there are things that stay for a very little while, but they trouble us a lot. Things with very less half-life say they're not very stable to exist, but they somewhat exist for us to explain them. So yeah, that is when you need your theories to be very precise. Yeah, we are done with the case of HF. Actually, don't really want to go into CO at this point because we have talked about a lot. So yeah. Now I'll show you a bit of the physical picture as now all that we have been doing for a very long time was just math. So I'll show you the simulation of how physically these orbitals look. Now when you see this, the z-axis, as you can see in this picture, the z-axis is along this, it's a horizontal line in this plane. You see these are two s orbitals of two nuclei combining. These essentially stay between the two nuclei. As I increase the brightness of this, you see a more similar picture to what you draw on the board. This is how orbitals stay. That is outrageously similar to how we are used to seeing the valence bond picture. Now when I go to say sigma star, these turn out to be very closer to the individual nuclei themselves. And something you see here that cuts out this. It's called a node. If we talk about a plane going perpendicular to this plane, that is going to be the nodal plane of this molecular orbital. You can play around with this, I suppose. Yeah, you can play around with the axes. So yeah, when we go to say sigma 2s, right? This is too much because it's farther away. So we see a broader sphere or a broader circle, as I would draw on a board. This is the picture of sigma 2s. These yellow things that we are seeing here are the nuclei, individual nuclei. Now, when we see, say, sigma star 2s, when we see sigma star 2s, you see this, say, node picture again. We see about pi 2px.
I think the axis is a little wonky. That's why it's showing.
Yeah, weird. The axis. Yeah. Now that is somewhat similar to what you see. That is somewhat similar to what you see. Because these are nuclei. There is no electron density here. They are not going to combine when you think of constructive interference. But these lobes, individual lobes, are going to combine, which is what inflates these balloon-like orbitals. Also, you see something that there is a nodal plane here as well. So it's not really a guarantee that you see a nodal plane only when you see an anti-bonding orbital. That also needs us to invoke the symmetries, as I talked about earlier. When you think about the, say, pi 2px star, yeah. This is something that this lobe stays close to the other nuclei, this lobe stays close to the other nuclei, and same goes for the symmetric analog of it. Now we think of, say, TZ. This is somewhat similar to the valence bond picture that you are used to see. This is something that is over, say, the usual balloon picture that you see. The blue phase is actually of the inner orbitals that have combined. The yellow thing is actually overlapped by that in the picture. Think of this. That is how sigma star easy looks. I'll decrease the brightness of it. You can see points where you don't see a bit of electron density that are cut in between. You also see this. You can see these screens where there is no electron density. That was because of the increased brightness that I lit. Was that visible? Yeah. So that is all that I wanted to show. I was trying to give you a physical essence of how these orbitals, how these molecular orbitals essentially look, and how outrageously similar they are to what people thought of without any computational techniques or the visuals that we have. So we can't say that theories go to a waste. They are very essential in reforming and addressing the discrepancies as well, because you carry the correct ideas with yourself and do additions to it in order to make it consistent with what you observe. That is something where I in today's lecture I have concluded. Thank you very much.